Okay, so the last little bit that I want to wrap up in differential equations in today's class is the third case, two distinct complex roots. And just a super quick review, we're talking about second order linear constant coefficient homogeneous equations. So we start by guessing a solution of the form y equals e to the RT, plugging into the differential equation, and we get this this simplified equation that we get AR. Uh, yeah. So for this choice of y, we get AR squared plus BR plus C times e to the RT equals 0. I just copied this and cut out some of the intermediate text. But at the end of all of this, we get the characteristic equation, AR squared plus BR plus C equals 0 for the roots of this exponential that we guessed as the solution. And as we said, this quadratic equation has two solutions, two roots, and those roots have three distinct cases. Discriminant bigger than 0 with two distinct real roots for r. The general solution looks like y equals a e to the r1t plus b e to the r2t, where r1 and r2 are the two distinct real roots. And that's our solution to the differential equation, where a and b are arbitrary constants. And then if we have some initial conditions, maybe y of 0 equals 0, y prime of 0 equals 1, or something like that, two different conditions that we can impose, we could figure out what a and b are and pick a member of that family of curves to satisfy that differential equation plus initial conditions, that initial value problem. The second case was discriminant equals 0. We have we have a repeated real root with multiplicity 2, so two repeated roots with value negative b over 2a. And in that case, we got the general solution by using e to the RT, e to the negative b over 2at, as one of our kind of component functions, or our basis functions, we might call them. And the second one just got a factor of t in front of it. So I just made the t bold so we can kind of see the difference. So a e to the RT plus b t e to the RT is the general solution for this one. And same note with adding two initial conditions can allow us to determine a and b and pick out a member of this family of functions as the solution to the initial value problem. And then case 3, discriminant less than 0, we get two distinct complex roots for r. Let's call the complex roots alpha plus or minus I beta. And a little bit of a spoiler, but just so that we have everything kind of in one place, the general solution will look like constant 1 times e to the alpha t cosine of beta t plus constant 2 times e to the alpha t sine of beta t, where alpha and beta are the real and imaginary parts of the roots. And in this case, C1 and C2 are the arbitrary constants. And again, same note that with two initial conditions, we can figure out what the two constants are and pick a member of the family of functions as the solution to the initial value problem. Now you might ask, how do we come up with this? Specifically, how do we come up with this out of a guess that looks like y equals e to the RT? And we're going to work through the math to do that. Some of it is going to be some material that we can't quite prove, but there are a few different ways of looking at this. One is we're going through this math, we're using some stuff that we can't quite prove at this point, but we're using it in order to give an argument as to why this is a sensible guess. Why functions like e to the alpha t cos beta t or e to the alpha t sine beta t are sensible guesses in this case. We're not losing any rigor here because, well, even if we don't prove all of the steps to generate the guess in the first place, so long as we carefully check the guess, right? Just like up here, we made this guess. We didn't really give a reason for it that was very precise. We just said, I mean, I need y prime, and y double prime to work well together in an exponential it seems to be a good guess. As long as we carefully check our solutions, then it's a solution, right? So how we got at the solution, we don't have to be super rigorous. So you can take on faith some of the stuff I'm saying. By the end of the course, we would be able to go through particularly this information on Euler's formula and understand it a little better once we talk about series and so on. And in fact, we'd even be able to see exactly why this is a reasonable guess. We'd be able to come up with an algorithm and come up with this guess for a second order equation based on series. So by the end of the course, we could actually come back and revisit this and get a deeper understanding of it. And realistically, what you would do is complete Calc 2 and then take a differential equations course where you'd look at a lot of this in a lot more detail. But by the end of the course, we would have the tools to kind of come back and revisit this in theory and flesh out some of these details that we're skipping over. But we're not missing any rigor here because we are still checking that these solutions do actually work. Okay, so looking at case 3, 2 distinct complex roots for R. And again, we're going to call those roots alpha plus or minus I beta, and alpha and beta turn out to be these two numbers. So we have a little bit of a problem that we need to figure out, in particular, what to do with e to the alpha plus or minus I beta times t. I have this imaginary number stuck in the exponent of this exponential function. And that seems, at the very least, very annoying, right? How do in the calculus that we're discussing, Calc 1 through Calc 3, we really don't encounter imaginary numbers often at all. And certainly we don't want imaginary numbers in our solution. So I want a real solution. I have a question that's a question in the, well, I actually don't have the formula written out here. Let me write it. It was AY double prime plus BY prime plus CY equals 0, looking for Y of t. All of this is real. I want solutions that are real. But a lot of times what happens when complex numbers pop up, not necessarily all the time, but a lot of time when they pop up, they're kind of an intermediate step. It's kind of like you're dealing with a real world problem, real valued problem. You kind of hit a stopping point where you say, it's tough for me to proceed from here. You kind of jump over to complex numbers, do some stuff, and then come back to real numbers, and then you have the solution. A lot of times that's how it works. That's how some integration formulas, if you look in the back of your calc book or whatever at integration table, some of those formulas are gotten that way. You take a real valued integral, you pass somehow into the complex space, it becomes really easy to solve, or at least easier or more tractable. And then you bring it back into the real valued side of things. So that's what we're going to do here. We're going to be using some imaginary numbers, but they're not going to show up explicitly in our solution. Okay, so Euler's formula is the main formula we're going to use here. I'll put it in bold, I suppose. And Euler's formula says that e to the I theta equals cos theta plus I sine theta. This is a pretty famous formula using theta equals, what is it? I think it's pi. Yeah. So we have e to the I pi equals cos of pi is -1 and sine of pi is 0, or e to the I pi plus 1 equals 0. And there's all kinds of people who really think that this is the coolest equation ever because it involves the two identities, the additive identity 0, the multiplicative identity 1, the exponential number pi, and the imaginary number. I mean, it's pretty cool. I don't know if I ascribe the same level of whatever, like almost religious significance that some people ascribe to this equation, but it's just a cool little thing whenever we choose theta equals pi in Euler's formula. This can be shown via the Maclaurin series for these three functions, which again is something that we'll see at the end of this course. And then if you wanted to come back and revisit this, you would see why this statement holds. It's not clear right now why it holds, but imaginary numbers are often tied to oscillatory phenomena. So whether that's in differential equations or linear algebra or whatever, a lot of times if we see imaginary numbers, we think of oscillations in some sense. So again, we want solutions of the form e to the alpha plus I beta times t, and we're not sure how to handle that directly, but maybe we can transform that into, well, this would be e to the alpha t times e to the plus or minus I beta t. Let me add a line here. And e to the plus or minus I beta t can turn into cos of beta t plus or minus I sine beta t. Cosine is an even function. It gets rid of the plus or minus. Sine is an odd function. The plus or minus just pass through sine. Okay, so we've made some progress. Our two y solutions are going to look like something like e to the alpha t cos beta t plus I sine beta t and e to the alpha t cos beta t minus I sine beta t. That might be our first thought. But again, we have imaginary numbers here. We might make a guess on the basis of this that instead of splitting this up as far as the plus or the minus part, maybe instead I should split this up in terms of the real part versus the imaginary part. So derivatives of functions that are complex valued like this, kind of, the derivative like this is just f prime of t plus I g prime of t. The derivative basically just treats the I like any other constant. So when I take a function like this and plug it into, say, a first or a second derivative, I'll be able to split apart all of the real bits and kind of collect them together, and all of the imaginary bits and collect them together. So if I have, let's call this, let's say f of t equals e to the alpha t cos beta t, and g of t equals e to the alpha t sine beta t, then y looks like, let's just say, f plus ig. Y prime looks like f prime plus I g prime, and y double prime f double prime plus I g double prime. When I plug this in over here, I'm going to get a f double prime plus b f prime plus cf plus I times, and then similar thing for g. A g double prime and this has to equal 0. In other words, 0 plus 0i. So this bit has to be 0, and this bit has to be 0, telling me that f and g are independently solutions to my differential equation. I mean, it's just a little bit of scratch work. Like, I'm not going through this super carefully, but we can see that coming from here, the real part if I can select it, the real part, the cosine part, as well as the imaginary part, the sine, have to individually be solutions to the differential equation if the overall function is a solution. So instead of thinking of my two solutions being like the positive bit and the negative bit, or the plus part and the minus part, I can think of them as being the real part and the imaginary part. From there, I can build a general solution, constant times the real part, plus constant times the imaginary part. I've got rid of all of my imaginary numbers. This is a real function, just has exponentials, sines, and cosines. There are no imaginary numbers in this general solution or anything like that. But I think this is going to be a general solution to my second order equation in the specific case where I have complex roots. Now it's kind of a side question. So we got to this behavior or this solution one way. We got to it in a very mathy way using Euler's formula, just kind of following our nose and saying, how do I handle e to the alpha plus I beta times t? And Euler's formula, we use that. If we didn't know Euler's formula, and if we didn't want to do all of this complex valued stuff, could we have maybe intuitively guessed this solution? I think this would be fairly challenging, but I think it would be possible. Remember our initial application. What did we want to model with this? Now, we're choosing to model something with this equation. Again, it is a model, so we can only take this analogy so far, but examining, if we say, okay, our model for a mass spring system, the mass spring system could have this type of behavior, and we see that pop up in one case of our model, or maybe this other type of behavior, we see that in another case. Or maybe it could have a third type of behavior. Well, I haven't seen that pop up in a case yet. Can I guess that maybe one of the cases ought to be a type of behavior that I would experience in the real world? We can make that guess. That's not a mathematically rigorous argument. Our model might just have a shortcoming that it doesn't work in that situation. But this can lead us to ideas, right? So if you're observing something and it leads you to an idea, and then you carefully and rigorously prove that idea, that's fine. So we know in our mass spring system, we have let's say this is equilibrium. We have a couple behaviors. We could stretch the spring and let it go, and maybe my mass spring system is pushing through a really thick fluid. So my position over time just looks like this, like an exponential decay. And hey, that looks a lot like maybe something like that. Maybe stretching my mass spring, my mass, I'm stretching the spring, I'm pulling the mass to the right. It's going through a really viscous, really thick fluid, and I give it a really hard push to the left. I give it a lot of momentum to start with. Maybe it can actually make it to the other side of equilibrium, but at that point, it's just compressed the spring, and the spring isn't all that strong relative to the thickness of the fluid. Maybe I have one extremum, and then just an exponential decay to the equilibrium from the other side. That might be a behavior that's, I don't know, maybe taken care of by something like this, right? An e to the minus rt times like a 1 plus t, that could have a single extremum. What I don't see anywhere in cases 1 or 2 in these general solutions is the kind of solution that I would expect from a mass spring system. The kind of solution that either goes like this, or maybe more likely in the real world, something like this, an oscillation with amplitude decaying to 0. So I have a decay in the amplitude along with an oscillation. if I think, okay, number one, I'm looking for a type of function that has an amplitude that decays along with an oscillation. The oscillation is probably going to make me think of trig functions, and the decay might make me think of exponentials. And that also meshes with the idea that I need to use functions where the derivatives kind of work nicely together. I don't want to use like a logarithm or something like that. That's derivatives are not going to look like it at all. But exponentials and sines and cosines, they kind of work pretty nicely together. Right? Their derivatives kind of look like themselves. So maybe I'm on the right track here, and maybe I would eventually come around to something like that, right? Or e to the alpha and sine of beta t. So I have an oscillatory bit taking care of the oscillations, but I just know from experience how these kind of things, mass spring system or like a pendulum or something like that, I know that the oscillations die out over time because they lose energy due to friction and heat loss and maybe even a little bit of noise or something like that. And I might guess similarly, could I use, instead of sine, could I use a cosine? Right. So I might be able to intuitively guess the solution based on the previous solutions that I found, and based on the fact that I expect this model to do a decent job of modeling something like this based on the Newton's laws and so on that we talked about before, and that I don't see this behavior anywhere in any of my other cases. Again, this isn't a guarantee that this would be the solution, but this might give us an idea, jumping back and forth between the model and the physical world that we expect it to model. It seems to model this or that scenario well. I don't see in the math anywhere where it models an oscillatory scenario, and those are the scenarios I expect to see in the real world. Could this third case be where that oscillatory scenario is hiding? And indeed it is. So we could have guessed the solution, but I think it would have taken, it would have taken a good bit of effort to guess it, but we maybe could have. We could have, in theory, maybe avoided this discussion of complex Euler's formula and so on in complex numbers, and just kind of intuitively guess the solution based on the mass spring system analogy. Okay, so let's just go through this example. Y double prime plus y prime plus 9.25y equals 0. And we have a couple initial conditions, but let's start by solving the differential equation. So I guess y equals e to the RT. I know this gives me the characteristic equation. Well, two derivatives from y double prime pops out in r squared. One derivative in r plus 9.25. I'm always kind of tempted to write an r here, but remember, this is just 9.25y, 9.25 e to the RT. Remember, this would be e to the RT equals 0. But then we know that the e to the RT just divides out. So we get our characteristic equation. R squared plus r plus 9.25 equals 0. And 9.25 is 37 over 4. So what is r then? It's negative b over 2a, negative 1/2, plus or minus some stuff over 2, square root of b squared, square root of 1 squared, minus 4 times a times c, 37 over 4. So r is minus 1/2 plus or minus square root of 1 minus 37 over 2. Oh, yeah, 1 minus 37 over 2. That's square root of negative 36. So that's I square root of 36 is 6 over 2. And after all of this, we get R equals negative 1/2 plus or minus 3I. I see that making this solution correspond to this formula up here, alpha is the real part, beta the imaginary part. So alpha negative 1/2 and beta is 3. And I know my general solution is constant e to the alpha t cos beta t, and then same thing with sine. I'll use constants a and b because they're a little easier to write. And this is my most general solution to the differential equation. I could factor out an e to the minus 1/2 t. That would make it a little simpler. I could even wrap this under a single trig function, a cos 3t plus b sine 3t, since they have the same frequency. I can make it a single trig function with a phase if I wanted to, you know, a e to the negative 1/2 t times, say, cos of 3t plus, c or something like that. So a lot of different ways that I could write this, but I'm going to leave it in this form. This is a family of functions. I would like to pick out the specific member of this family of functions that satisfies the constraint y of 0 equals 2, y prime of 0 equals 8. So we do have oscillations with damping. This e to the minus 1/2 t is taking the oscillation's amplitude to 0. And these correspond to initial position, where 2 units stretched from equilibrium, and initial velocity, where giving the mass a whack in the positive direction of 8, whatever units it's going to be. And then we let the system evolve from there. So what is y of 0? Well, the e to the 0 stuff goes away. I have a times cos of 0 plus b sine of 0 is 0. Y of 0 is just a. That's not too bad. That's got to be 2. Now to find y prime of 0, I have to do 2 derivatives, 2 product rules. So I'm going to have 4 terms, but a bunch of them are going to go away. Okay, so for my first, my initial first term, what are my 2 terms from the product rule going to be? If I differentiate the cosine, I get a sine. When I plug in 0, that goes away. When I differentiate the exponential, I get negative 1/2 e to the negative 1/2 t times a times cos of 3t. But this gives me negative 1/2 times a e to the 0 cos of 0. That's just 1 times 1. So just negative 1/2 a. That's all I get from this first term here, differentiating and plugging in 0. What about my second term? When I differentiate the exponential in the second term, I'm left with a sine, and sine of 0 is 0, so that term goes away. When I differentiate the sine, I get a cosine. So my sine of 3t differentiates the cosine of 3t times 3, so I get a 3b e to the negative 1/2 t cos of 3t, but plugging in t equals 0 makes the exponential and the cosine both 1. So y prime of 0 is negative 1/2 a plus 3b on one hand, and on the other hand, that's got to equal 8. Or plugging in 2, we get negative 1 plus 3b equals 8, which says I think that b has to be 3. We get negative 1 plus 9 equals 8, and that looks good. So what's my specific solution, my specific member of the family of curves that satisfies the differential equation and the initial conditions. So A is 2. And B is 3. And again, you can make this a little nicer by factoring out an exponential, maybe even a little nicer or just different by wrapping this under a single trig function. But we'll just kind of leave it here. Any questions on anything in diffie-q? Okay, so the complex case, again, not super qualitatively different than the previous ones, but just the form of our general solution is quite a bit different, right? But qualitatively speaking, we have a form of the general solution, just like we had a form of the general solution for the other two. We use our differential equation to figure out what are the parameters alpha and beta. We get a general solution that satisfies the differential equation. Sometimes we're just done there. And sometimes we have initial conditions to go along with it, where we want to pick out a member, a single member of that family of curves to be the solution that satisfies the differential equation as well as the initial conditions. Okay, so moving on then to chapter 10, if there aren't any questions in differential equations. Moving on to parametric equations and functions. Let me bring up my notes here as we're switching gears. All right. So kind of completely shifting gears here to a completely different topic, parametric equations. So let's talk about some basic ideas. What's the basic idea here? Well, we have functions like y of x that might look like this, right? That we might want to use as a model and say, when one variable is, say, x equals 3, another variable y is maybe 4, something like that. Our standard kind of form of a function. And these work great a lot of the time, right? But what if I wanted to think about maybe x and y as two positions in a 2D plane? Maybe I'm talking about a ball rolling over the surface of a table. Well, to have a regular function, a y of x type function, it needs to be the case that for each input, each potential input, there's at most one output. But is that really the right way to think about, say, a ball rolling around a table where I just have an x-axis and a y-axis? Or maybe, if you were thinking of a CNC machine that's, drilling out a certain pattern on a piece of metal or a piece of wood, is it really that, does it have to go left to right and can never go backwards? Well, I don't think that's really a good model for something like that. Maybe we have a function like this that we would like to model. So if I try to say for a given input x, what's the output y? I mean, I guess sometimes I can do that, okay? But sometimes that doesn't work so well. So if I think about something like a ball rolling on a table or a CNC machine kind of drilling out a certain pattern, what would be a better way to model that? What's really the functional relationship here? It's not so much one spatial dimension versus another. It's kind of like in time, right? At a certain point in time, the ball is at a certain point on the table. Or at a certain point in time, the CNC milling bit is at a certain XY location. Let's forget about Z. But yeah, the bit is at a certain XY location at a certain time. So instead of having a function like this, where I, list some X's and they give rise to certain values of Y, a normal function, instead, maybe it would be valuable to think of a third variable, T, where I say, okay, at certain times, at a certain time, I have my ball on the table at a certain position, X and Y, that the time that I choose gives rise to both the horizontal and vertical location. Or that X is a function of T and Y is also a function of T. So X and Y are still related to one another through this common variable T, time, right? There's no time at which I'm at that point. There's still some relation between, some connection between X and Y, but it's not so strict as to be a kind of a functional relationship. So I might come over here and say, well, at say time 0, the ball or the bit or whatever was at this XY point. Maybe X equals -3, Y equals 4. At time 1, the bit was at this point. At time 2, time 3, 4, 5, and so on. So I have a functional relationship between, say, T and X. If you tell me what time you're interested in, I could tell you exactly what X point you're at that time. I have a functional relationship between T and Y as well. If you tell me I'm interested in time 4, I could say you were at this Y coordinate at time 4. Even though there's not necessarily a functional relationship between X and Y. If you say hey, I was at this X coordinate, I'm not 100% sure what Y coordinate you were at. And it's also, in this case, more natural maybe to know where this bit is going. Maybe if I had 2 bits trying to work together, not that a CNC milling machine would actually have 2 bits, but, or if I had 2 balls on the table or something, or maybe 2 planets or comets or whatever going around in space, and I wanted to know, do they actually collide? If one of them, for whatever crazy reason, had this path, another had this path, would I say, oh yeah, they collide here and here? Well, to collide, they have to be at the same point in space at the same time. I don't care if their paths cross if they don't cross at the same time. So if the arc that they travel along crosses, but they're never at those points of intersection at the same time, we don't have any collisions. So there are situations like that where time is very crucial. It's important to know the time that we're at different locations. Okay, so how can let me maybe move these over a little bit. How can I think about the relations X of t and Y of t? Well, if I imagine as I progress forward in time, what does Y look like? Note my different variables here. Now I'm graphing Y as a function of t, not Y as a function of X. This black curve over here, the loop-to-loop, is a Y as a function of X, but Y is a function of t when t is 0, Y is like here. When t is 1, Y is a little lower. When t is 2, Y is a little lower still. And then when t is 3, Y goes up. When t is 4, Y goes up again. Seems like it reaches the max at 4. At t equals 5, it comes back down. So Y might look like this. Something like that. This little blip here on that axis was just a mistake. I didn't mean to actually touch the thing there. But yeah, so Y of t might look something like this, or maybe if I draw it a little more cleanly, Y might look, so I went down, up, down, and then up again. I need another little piece over here. Maybe something like that. So maybe y is some kind of, I don't know, trig function or something. And then what would x look like in terms of t? I'm going to draw this one a little funny. I'm going to draw it kind of sideways. Here's the t-axis. Here's the x-axis so that we can kind of trace along what's happening with x. And we'll have like t equals 0, 1, 2, and so on. So what happens to x as t evolves? X starts, need to give myself a little more room on the left here. I'm not doing a good job of planning ahead for my graphs. But I see that when t is 0, x starts way off here to the left. When t is 1, x moves to the right a little bit. So when t is 2, x moves to the right a little more. When t is 3, x moves to the right a bit more still. When t is 4, x moves to the left. 5, it moves a little further to the left. 6 further to the right, 7 to the right. So it's going something like that. But remember, this is kind of a little funny way to graph this, right? We're graphing t that we're really thinking of as the independent variable on the vertical axis, and x, the dependent variable on the horizontal axis. It's a little funny for us to interpret. How do we flip things so that it looks better? Well, we just flip it over this 45-degree line. So what would x of t look like? Kind of in a graph that's a little more familiar for us to look at. X is positive and negative, so it's going to come down a little bit. And what was it? When t was 0, x was negative quite a bit. When t was 1, x was a little less negative. And then 2, it was positive. 3, it went up a little further. So it goes something like this. I'm not being super careful about drawing it, but so maybe y is some kind of sine function and t and x is some kind of cubic related to t. So maybe I have something like y of t equals, I don't know, cos of t minus, or let's say just t minus 1 or something, plus 1, and, x is maybe some kind of cubic, 3t cubed minus 2t plus 1, or I'm making these up, but you get the idea, I think. Now, typically, we wouldn't be going this direction. Typically, we might be going the other direction. We might be given a relation like this. We might think, how would these x of t and y of t individually contribute to the overall picture? And then we might try to stitch them together to get a picture like this. Right. And again, these are just made up. It certainly looks like this could be a cubic and some kind of oscillating function like a sine or cosine, but I'm just throwing something out there. So that's the basic idea of parametric equations. Sometimes we want to use a parametric equation because we have a fundamentally non-functional relation like this, where maybe it just makes more sense to use a parametric equation. Sometimes we actually have a component of time, like something is moving about in two-dimensional space throughout time, and it's very sensible to model it that way, where we're interested in not just its location, but also the time that it's at the location. And sometimes, like I mentioned, if we're looking at collisions or something, the time is actually a crucial element. Knowing that, are we at the same location at the same time, or is it just that we're at the same location at two different times, and we never actually collide. I was going to say we never actually cross paths, but that's not quite precise enough, that colloquialism. Now, sometimes we want to go the other way. Sometimes we say, maybe I do have, if I'm looking at this up here, maybe I have a situation where, let me just move this down a little. Maybe I do have something like this with my different t's on it. And maybe for whatever reason in the application that I'm interested in, I really don't care about t. I really don't care about the time that I'm in a certain place. I am happy to just know y of x. In something like this, it seems like even if I started with a parametric equation, I might be able to recover a functional relation between y and x. That's the idea of eliminating the parameter. So we'll go through this example. That'll probably take us to the end of class today. Then we come back, we'll continue on with chapter 10. So here I would like to move from a parametric equation where I have x and y are indirectly related to this through this common variable t, to something like a y of x, to a direct relationship between x and y, where I eliminate t, the time variable. And as an aside, I mean, often I just call t time, but t doesn't have to be time. It can just be a meaningless variable. It could be something else that relates x and y. But a lot of times we just think of it as time because it's convenient. Here I might note that this seems very circly. And I might note that x squared plus y squared this is a squared times sine squared of t plus cos squared of t is just 1. So I ask myself, how can I get rid of the t bit here, the sine of t and the cosine of t? How can I eliminate this variable? I can go from what? 3 unknowns, x, y, and t, in 2 equations, down to 2 unknowns in 1 equation. Can I eliminate 1 parameter and get rid of 1 equation? And I can. This is, in some sense, like a nonlinear system problem. I get x squared plus y squared equals a squared, a circle centered at the origin with radius a. The benefit is that sometimes this can be simpler to work with because I don't have the t to deal with. The detriment is that I lose the information about t. If I say, okay, at some time I'm here, what time am I there? I don't know anymore. I would have to go back to my parametric equations to figure that out. But if I want to get a graph, I'm much more used to looking at functions that just have 2 variables and 1 equation and knowing what the graphs of those look like. So a lot of times I might want to eliminate the parameter, draw the graph, get the picture, the total path that the particle or whatever takes, and then come back and figure out what are the time, kind of the time points later on. When am I at this point or that point at what times? So when we come back, we will, because we're out of time today, when we come back, we'll wrap up this problem. We'll kind of tie in the rest of those details with what time are we at, what XY location next time. And then we'll continue on with sections 10.1 and 10.2 up through 10.4.